Hey, don't hate me because I'm 192.168.1.151. By the end of this session, we will be able to explain how the SDA control plane functions via the Location Identifier Separation Protocol, or LISP. Yet another mouthful out of this SDA architecture conversation, so thank you, Cisco, for that. Within the world of networking, we've had a conundrum for some time, and that is that my identifier, the way you identify me on the network, is by my IP address. For example, if you want to stop me from getting to a server on your network, you would block my IP address, or maybe block the entire user subnet. But the problem with this is that my identifier, who I am, who you view me as, can change. If I roam over to the other side of the network, my IP address will be different, and therefore I will be different as far as the network is concerned. Well, we need to solve that problem. We need to make sure that wherever I am, I can be identified, and Lisp is how we're going to get there. As mentioned, here's the problem that we face with traditional networks. As far as the network is concerned, me, equals my IP address. And just as true, my IP address equals my location. In other words, if I'm my IP address, but then I change locations, my IP address changes, and so I'm no longer me. That's a problem. So here's the solution. We're going to separate the location from the identifier. We're going to make the IP address not equal to the location, and therefore any IP address can go anywhere. Now, if you're like me and you're a traditional network engineer, you're already scratching your head on this. Like, wait a second, how does this work? And the way it works is with a protocol called LISP, Location Identifier Separation Protocol, which is an acronym that actually describes what it's doing. It takes the location and the identifier and it separates them. So let's look at this network that I have here drawn in the middle. And with traditional networks, a layer 3 separation, a layer 3 boundary means that our subnets can't be spread among different locations or different nodes. So for example, I might have subnet A off of this switch and subnet B off of this switch here on the right. So if I am a user and I connect into this network, I might get an IP address that, let's just call it A1. And then maybe through wireless roaming, or maybe I actually pack up my laptop and I go for a drive and I show up at a different building entirely, and now I'm connected into this location. Well, my IP address can no longer be A1. And that's because subnet A lives over here. All of the other network devices know to send subnet A down to this layer 3 location. So we can't just have A1 living over here on the right, because all of the traffic for A1 will get sent to the wrong location. So here's what Lisp is going to do. Lisp is going to allow all of the subnets to live at all of the locations. So let's say subnets A and B live in every single location here. And this would apply if we have more than 2 subnets as well. So if we had 30 subnets, all of them would live at every single location. Already you're thinking, okay, well wait, Jeff, if they're all going to live everywhere, this can no longer be layer 3. This is going to need to be layer 2. But hang on, because Lisp is going to help us with this. What Lisp is going to allow us to do is to track where all of the endpoints are in the network, which means that if I'm connected here and I receive IP address A1, Lisp will make sure everybody in the network knows that if you're going to send traffic to A1, it will arrive on the right switch. And then let's say I move over to this new location over here, and I still have IP address of A1. Well, now the network is going to know to send the traffic. Instead of sending it down here, the network will know to send it here. Lisp refers to an endpoint as an endpoint identifier, EID. And it truly tracks every single EID in the entire network. So yes, that's a lot of endpoints that we need to track. Now, Lisp is not just tracking the endpoints, it needs to know where those endpoints are. And the where is what we call the routing locator, or RLOC. The RLOC is typically a loopback address on one of these network devices, which are typically layer 3 switches or potentially routers. Therefore, what we're really doing is binding endpoint identifiers with RLOCs in the network. And this is going to be stored on something we call a mapping server. Now in SDA, we've already talked about this. This would be the control plane node, because it's tracking all of the endpoints in the environment and mapping them to individual switches in our campus fabric. Now, in order to facilitate this, we do still need a little bit of help. We can't just leave this alone as a layer 3 fabric. It's going to cause all kinds of routing issues and duplicate subnets, and we're really going to send all of our traffic to the wrong location. So how do we know where we're going in this network? What we're going to do is we're going to build a fabric of tunnels. These tunnels are going to link all of the network devices where we have endpoint identifiers attached. In other words, this in software-defined access would be our fabric edge nodes. Now all these edge devices have ways of communicating with each other. So when a packet comes in destined for A1, we can send that to the appropriate switch. We will check in with our mapping server to find out which switch, or really which RLOC, we need to send this to. And the RLOC is, again, the identifier of that tunnel endpoint. And so we're going to send it out the appropriate tunnel, and that will land with A1. Now, unfortunately, there is a problem here that we still need to address. LISP, as a protocol, has two components. It has a control plane component, which we've described here with the mapping server, and it has a data plane component, which is a tunnel mechanism. The problem is that these LISP tunnels are layer 3 only. And so the scenario that we've drawn out here, which is an SDA example, can't actually function. Our A1 can't move over to another location because these subnets aren't capable of being split up. So what was the point of LISP? Well, everything we've talked about the control plane elements of LISP, we still need in an SDA fabric. We want to rely on those EID to RLOC bindings. LISP simply falls short as far as the tunnel mechanism is concerned. And so if we replace the tunnel mechanism, then LISP is going to do exactly what we need it to do in the SDA space. And that is where VXLAN comes into play. And with that, you are now able to explain how the SDA control plane functions via LISP. I hope this has been informative for you, and I'd like to thank you for viewing.